Hello and welcome, everybody listening, especially Professor Mitchell. Welcome back, and this should be the final culmination of the whole LiDAR scanning experience. The last video was about gathering all the separate face LiDAR point clouds and collecting them into one whole one. This shows the final product. Over here, we have our four-faced IREB sign outside the Brendan IREB CS building. And if you were to see it in person, it has its name right over here. Now, this current model shows each face, and the color gradients shows wherever I made a cut. So you can tell that here there's a lot of modification to make them fit together. Here, I was lucky and based the curve on it. There were a couple minor modifications here and there, but all in all, it is one quite cohesive model. We can get a better look of it if we use the color option and use the height ramp. And if we use a Z height ramp, we can see the ground over here, the raised bench over here, the curves, and so on. And if we were to use the other axis, let's say, for example, the y-axis, we'd be able to see the different depths, right? Blue is the closest to us, red is the farthest, and green shows that it more or less falls within the same y-axis, right? But here comes the next step, which is creating it into mesh. Right now, we just have a couple of thousand points that make one thin cloud. This cannot be thrown onto a 3D printer or projected in a three-dimensional way. So we're going to utilize Cloud Compare's own mesh making software. And to do that, we need to do a couple steps. First one is pick our point cloud and add normals to it. So we're going to compute normals. We're going to set the orientation and use minimum spanning tree. Right? The surface model, I was testing a bunch of them and I found triangulation often work the best. But we do face an issue that you're about to see very, very soon. Once we set the, give it a sec, there we go. Once we set the normals, we can see that it gets darker as the normals projected onto each point over here. The next step is to then use the Poisson Recon plugin, activate it, activate output density as an SF, and you can make this greater and it will lead to like a better quality print, but your computer will get slower. It will take longer to calculate. And for this one, as you'll see in a second, we don't want that. So when you run it reconstructs it, gives it a sec, and then you get faced with this. What on earth is this? And I faced a similar problem with MeshLab. The way around it, I found, is that right now the software sees thousands of tiny points, and there is an algorithm it uses to try and find the nearest point. But with them being so cluttered and so overlapping, it doesn't know whether to go up, left, right, or deeper into the model. It doesn't know where the confines of the model are. The way I found to overcome that, let's remove this really quickly, is, and let's just use this for now, is to first, we're going to subsample this entire thing. The way we're going to do it is to randomize the method. We don't want any holes in our model. Randomize it. Let's pick a tiny bit more than this. There we go. And what this does is basically flushes out a bunch of the excess. As you can see, it's a much thinner point cloud. Still keeps the relative shape, which is why we kept it random. But it's a lot cleaner to make like straight triangles, right? From here, we're going to compute the normal. Keep it as such. It's going to build the arc tree, compute, yada yada yada. And then from here, we try the same thing we did. Reconstruction takes a lot less, but you can find it uses a much cleaner final result. Now, you can see there are bumps, and that comes from differences in height levels and how the mesh wants to make everything curved. And you can see I trimmed off some of the noise over here from the earlier one. If I was to show this one, as you can see, I trimmed this section, and this section, simply because it caused greater noise. However, it is not a bad mesh. There are ways to fine-tune it. Focus that the majority of the points are removed from the center and not from the edges, such that the edge is all sharper and get better point data, basically. If it's more regular, if it's more hollow on the inside, the nearest connection would be the one right next to it, creating a pretty smooth wall. Right now, because it is irregular, it is sort of being all over the place, and we mitigated it by reducing the density. From here, we now have a mesh that we can save, and from then on, we can then export it and turn it into our very own 3D print that I'll be personally delivering to Professor Mitchell for that sweet extra credit. Thank you so much, and this was fun.